So let's switch to the next one. It's polymerization. The photopolymerization occurs when a photopolymer resin is exposed to light of a specific wavelength. It's visible wavelength or UV light in most of the cases. When you expose this resin to the light, the specific chemical reactions takes place, solidifying the resin. So during the solidification, the monomer carbon chains are activated and make it solid. Due to this reason, due to the chemical nature of this process, these materials are unrecyclable comparing to the FDM process when you can recycle your thermoset polymers. Of course, the quality of your parts will depend on the number of these cycles in FDM, but it's possible, which is not in the photopolymerization. So photopolymerization can be divided in 3 categories. If we talk about the scientific ones, it's the 4 category. It's stereolithography, direct laser light processing, and continuous direct light processing. So here the resin is solidified by a laser. Here this resin is solidified by a digital light projector. And in continuous DLP, the solidification by DLP is inhibited by the oxygen. So let's also take a look on the scheme. How does this process work? Here's additional some text for your study, so you can check it by yourself while we will move further and discuss the main setups in stereolithography 3D printing. So there are generally 2 schedules. It's the top-down SLA, which have the laser source above the tank, and the part is built facing up. The build platform begins at the very top of the resin and moves downward after every layer. So sorry, but this text is going for this picture. And the bottom up SLA printers takes place, place the light source under the resin tank, and the part is built facing upside down. So the tank has a transparent bottom with a silicon coating that allows the light of the laser pass through the window and stops the curing resin during the curing of the resin from sticking to the window. So let's take also take a look on the video on how does these processes takes place. So let's start from top down.
Stereolithography is a rapid prototyping process used to create parts from 3D CAD data in a matter of hours. SLA is a highly accurate additive manufacturing process and may also be referred to as rapid prototyping or 3D printing. Models created with this technology are typically used as concept models for form and fit studies or as master patterns for molding techniques. The SLA process begins when CAD data is sliced into thin cross-sections or layers, typically about 0.006 of an inch thick. This data is then transferred to an SLA additive manufacturing system containing a vat of UV curable photopolymer. The machine begins to build the part 1 layer at a time. Each layer is constructed from an ultraviolet laser that is directed by X and Y scanning mirrors. As the laser traces the cross-section on the surface of the resin, the liquid material is hardened on contact. Once a layer is complete, the build platform is indexed down to make room for the next layer. A recoater blade moves across the surface, ensuring a thin coat of fresh liquid resin is evenly spread over the object. The laser continues to trace and form each layer atop the previous layer, building from the bottom up. The completed part is then carefully removed from the liquid and separated from the platform. A chemical bath removes excess resin, and the part is cured in an ultraviolet oven. Any support structures are removed at this time. With numerous hand sanding and professional paint options available through service providers such as Solid Concepts, stereolithography has become an excellent economic choice for rapid appearance models. A wide variety of industries have embraced SLA, including medical, automotive, entertainment, aerospace, and consumer products.
So let's take a look on the next one. It's also on stereolithography, but for bottom-up method. So this is the desktop printer called Autodesk Ember.
Here's a demonstration of high-speed printing on Ember. For the first 11 layers, the tray uses a sliding mechanism to separate each layer. However, after that, there is enough space between the build head and the tray window so that the suction force is minimal. The Ember now pulls directly upward after each layer. This part is printing 24 times faster than a print using the standard Ember resins and print settings. The resin is specifically formulated to print thick layers, here 250 microns. Thick layers are difficult to print on stereolithography printers because the light must penetrate deep into the resin without scattering and curing adjacent negative space areas. It prints at about 440 millimeters an hour. This high-speed printing is a great way to get a quick prototype in minutes that would typically take several hours. After about 17 minutes, the print, which takes up the entire build volume of the printer, is complete. Check out the Instructable linked in the description to learn more, or visit ember.autodesk.com.
What's interesting about this video is that this video combines two very important things about stereolithography bottom-up printing. So the one, as the video said, the first 11 layers was printed by pushing the platform to the side, which is necessary due to the big suction forces which takes place when your building platform is close to the transparent window. While after that, by combining few factors, one is the big layer height, which enables the possibility to get the layer as thick as 250 microns, which is enough to reduce the suction forces. The other is the choice of geometry, which is not planar and also very thin. All this together enable this printer to work in the case as continuous DLP printer works, and to increase the printing speed in 20 times. So let's discuss it a little bit more.